Welcome everyone. Today we are doing a deep dive into Lakeflow Jobs, Databricks' native orchestration engine for building, scheduling, and running reliable data pipeline at scale. This isn't a surface level overview. We are going to cover the architecture, how Lakeflow Jobs actually works under the hood, the best practices that separate production grade implementation from fragile hobby projects, and the pitfalls I see teams fall into repeatedly, and how to avoid them as well. So, whether you are building ETL pipeline, running a machine learning workflow, or orchestrating complex multitask DAGs, Lakeflow Jobs is the engine that ties it all together on the Databricks Lakehouse. Let us get into it. Now, we need to start with this question. What is Lakeflow Jobs? Now, Lakeflow Jobs is Databricks' native first-class orchestration engine. So let me be precise here. It is about what that means, because orchestration is an overloaded word. Now, at its core, Lakeflow Jobs lets you define a DAG, a directed acyclic graph of tasks that run in a specific order with dependencies between them. So those tasks can be notebooks, Python scripts, JavaScripts, SQL queries, dbt projects, or machine learning models training run. So you compose them, define the dependencies, set the compute, and Lakeflow Jobs handles the rest. Now, what makes it distinct from Airflow or ADF, the Data Factory, Azure Data Factory, is that it is native to Databricks. There is no separate infrastructure to deploy, no Airflow DAGs to maintain in a separate code base, no authentication complexity between your orchestrator and your Databricks workspace. It is fully integrated. So the orchestration layer, the compute layer, and the governance layer are all one system. So 4 things I want you to highlight here is this multitask workflow, flexible triggers, serverless compute, and built-in observability. We'll go deep on all of these in the slide ahead. Now, let me walk you through the architecture from top to bottom. At the very top, you have your trigger layer, yeah? Call it trigger layer. Now, Lakeflow Jobs supports 5 trigger types. A cron schedule for time-based execution, file arrival trigger that fires when new data lands in a storage location, API and webhook triggers for event-driven execution, and a continuous mode for near real-time processing, and also, of course, a manual runs for ad hoc execution. Now, below the trigger is the job itself. Think of the job as the container. It holds all the configuration that applies to the whole pipeline: retry policies, notification settings, permissions, Git source integration, and job level parameters. Inside the job, you have your task DAGs. This is where the actual work is defined. Tasks can be notebooks, Python scripts, SQL queries, dbt projects, or machine learning pipeline. The arrows between them define the dependency order. For example, task B does not start until task A succeeds. At the bottom is compute, and that is where a critical architecture decision gets made for every task. Serverless compute, job clusters, all-purpose clusters, or SQL warehouse. We will dig into this in detail shortly, but the rule of thumb is serverless for standard workloads, job clusters for large-scale or custom configuration. Now is the time for task types and compute. So on the left, task types, you have 6 options. You have the notebooks, the Python script, SQL script, or SQL tasks, DBT, machine learning or ML, and ML flow, and pipeline tasks. The key insight here is that Lakeflow Jobs does not force you to standardize on one task type. You can mix and match within a single job. So your ingestion task might be a Python script, your transformation might be SQL, and your machine learning query might be in a notebook. So that flexibility is a big deal. So on the right is the compute option. This is one of the most consequential choices you will make. Let me be direct here. For the majority of workloads, serverless is now the right default. No cluster startups, automatic scaling, pay per execution, second billing. If your workload runs on standard Databricks runtime, so use serverless. Now, job clusters are still the right choice when you need custom Spark configuration. For example, init scripts, GPU support, or a specific library version not available in serverless runtime. They start in 2 to 5 minutes, of course, which introduces latency, so factor that one into your SLA design. Now, the SQL warehouses are specifically for SQL tasks. They are optimized for query pattern and use the Photon engine, but they are not the right choice for data transformation pipeline. Now, one pitfall I see constantly is teams spin up all-purpose clusters for job because it is a familiar option. So all-purpose clusters are expensive. They are designed for interactive development, not production jobs. So always use job clusters or serverless for scheduled jobs or workloads. This is a time for scheduling and triggering or triggers time. So let me talk about how jobs get triggered and then about dependency conditions. For example here, cron scheduling is the most common trigger type. So one important note here is always specify your cron expression in UTC, not local time. I have seen pipelines in UK clients break after BST or GMT transition because the team wrote a cron expression relative to their local time zone. UTC is your friend here. Now, file arrival triggers are powerful for event-driven pattern. Rather than pulling on a schedule, the job fires as soon as new data lands into a specified storage path. Importance is use the bounce setting to prevent the trigger firing multiple times if files arrive in quick succession. So the API triggers are what unlock CI/CD integration. You can call the jobs API from Azure DevOps, GitHub Actions, or any external system to trigger a run with the custom parameter. This is how you build truly event-driven architecture. Now, task dependency. This is an underused feature. Most teams just use the default all success condition, which is often correct, but the other conditions are genuinely useful. At least one success is useful for fan-out patterns where you need some parallel tasks to succeed, but not all. So all done lets you also create cleanup or notification tasks that run regardless of success or failure. So all failed means let you build proper error handling pipeline. Imagine a task that runs an alternative ingestion path when your primary source fails. Now, what are the best practices here? So let me walk you through 6 best practices I consider non-negotiable for production Lakeflow jobs. One is serverless by default. I have said it before, I will say it again. The the number of teams I see still spinning up job clusters for every workload when serverless would handle it perfectly is significant. Use serverless unless you have a specific reason not to do that. Number two is one concern per task. Yeah, the temptation to build a single notebook that ingests, transforms, validates, and serves data is strong, especially in early prototyping. Resist it though. Separate concern into tasks. So that is what enables you to retry just the transformation task without rerunning ingestion. So number three is never use all-purpose cluster for jobs. These are development tools, not production infrastructure. So I have seen teams spend 3 to 4 times more on a compute than necessary because they are reusing their interactive clusters for scheduled jobs. Now, number four is parameterize everything. The job that works perfectly today becomes a source of pain the moment you need to backfill 30 days of data. If your data or partition path is hard-coded, you will be manually editing notebooks under pressure. So parameters solve this for you. So don't forget it. If it is possible, just use parameters everywhere. That will save you a lot of pain and hardship in the future. Now, retry policies. 2 to 3 retries with exponential backoff should be the default for any task that touches external systems. Most transient failure resolve themselves. Yeah, so you need to have like 2 to 3 retries. Yeah. Now, number 6 is Git back source. This is the difference between a mature data team and an ad hoc one. When your job runs notebook version 7, rather than the latest thing someone saved, you have auditability problem, rollback capability, and proper change management. Now for the pitfalls. So these 6 pitfalls are not theoretical. I see them in real customer implementation regularly. Yeah. So pitfall number 1 is all-purpose cluster for jobs. We covered this in the best practices, but it bears repeating because the default behavior in many organizations is to use whatever cluster is available. The cost implication is significant here. Now, pitfall number 2 is hard-coded dates. This is insidious because it works fine in normal operation and only fails when you need it most. So during an instant recovery or historical backfill. So always externalize execution date as a parameter. Yeah? Pitfall number 3 is monolithic tasks. The symptom is that a task failure forces you to rerun everything from the beginning. The fix is task decomposition, which also unlocks parallel execution. Yeah. So pitfall number 4 is no retry policy. Transient failures are a fact of life in distributed systems. So a job that fails permanently on a 30-second network timeout is a job that will page you at the 3 a.m. unnecessarily. So pitfall 5 is no timeout. I have seen jobs hang for 8 hours because a SQL query was waiting on a log. With the timeout configured, the job fails fast and you get alerted immediately rather than discovering it the next morning. Now, pitfall number 6 is concurrent run overlap. This is a subtle one. If your job takes longer than it is scheduled interval, you end up with multiple instances running simultaneously, potentially causing data corruption or resource contention. So set your concurrency policy to prevent this. Well, monitoring and observability. So Lakeflow Jobs has a solid built-in observability layer, and Using it properly is what separates teams that find out about failures from their SLA breach notification versus teams that find out from users. So run history gives you a complete audit trail. So every run, every status, every duration. So you can filter by date range, see exactly which task failed, click through to the Spark logs and event timeline. So no external tools needed here. Task level metrics are where you find your bottlenecks. If your job is taking 90 minutes and you are not sure why, the task metrics will show you which specific task is consuming 85% of the time. That is your optimization target. Now, repair run is one of the most underused features in Lakeflow jobs. When a job fails at task 8 of 12, most teams rerun the entire job. Repair run lets you re-execute only from the failed task, preserving the output of all successful upstream tasks. For expensive jobs, this can mean the difference between a 30-second recovery and a 2-hour rerun. So on alerting, configure duration warning threshold on every production job. This fires an alert when the job is taking longer than expected. So before it actually fails, it gives you an early warning to investigate before the deadline is missed. Now, one recommendation is integrate your failure webhooks with your team's Slack or Teams channel. A job failure at 3 a.m. should wake the on-call engineer, not wait until the 9 a.m. stand-up. So that is very important. Git integration and CI/CD. So this slide is about treating your Databricks jobs as software, not as configuration that exists only inside the Databricks user interface. Now, the Git integration feature connects your workspace to a Git provider, the GitHub, Azure DevOps, or GitLab. Once connected, your jobs reference notebooks by their path in the Git repository, not by their workspace path. I repeat, your jobs will be referenced by reference notebooks, the notebooks by their path in the Git repository, not by their workspace path. This means every change to a notebook goes through your normal Git workflow. Branch, commit, pull request, review, merge. Why does this matter? Because I have seen teams lose hours debugging a job failure that turned out to be caused by someone editing a production notebook directly in the workspace. No version control, no audit trail, no review. So Git-backed jobs make that impossible. So the job as code approach on the right takes this further. Using Databricks asset bundles, which replaces the older DBX tool, you define your entire job in a YAML file that lives in your Git repository. This means your job configuration is versioned, reviewable, and deployable through your CI/CD pipeline. You can promote the same job configuration from dev to staging to production with confidence. One deployment pattern I recommend is use Git tags for production deployments. Your CI/CD pipeline tags the commit when test passes, and the production job is updated to references that tag. Rollback is as simple as pointing the job to the previous tag. Let me bring this to life with a concrete example. A nightly student analytics pipeline at UK University. The job runs at 11 p.m. UTC every night, giving the data team time to resolve any issues before the morning dashboard refresh. The DAG has 7 tasks, starting from left. T1 ingest raw student data from student information system into the bronze layer. T2 runs data quality checks, row counts, primary key uniqueness, schema validation, If T2 fails, the entire downstream chain is blocked, which is the right behavior. T3 is transformation, the clean bronze data into the silver layer. T4 builds the student 360 gold dataset, joining demographics, attendance, LMS activity, and grades. So T5 runs the ML flow dropout prediction model and writes risk scores back to Delta. Now T6 and T7 runs in parallel after T4, using at least one success. So if the dashboard refresh fails, the email alerts still go out. And in the bottom left, T8 is an error notifier task with condition all failed. It sends an alert to the platform team if the entire ingestion chain fails. Now, the configuration table at the bottom shows the key parameters for each task: compute type, retry configuration, and the SLA expectation. Note that T5, the machine learning scoring task, uses a job cluster with GPU support. So because the neural network model requires GPU acceleration, so everything else runs on serverless. Now, this is a production-grade implementation pattern that has been running reliably for multiple institutions. Now, new features, advanced features, that is. And one is the three advanced features that unlock significant capabilities. One is you have measured the task. So I'm going to just to mention three. There might be others, but these are very useful features, even though they're advanced. So task value is a lightweight in-memory communication channel between tasks in the same job run. Yeah. Now, instead of writing intermediate results to a delta table just to pass a count or a flag to the next task, you use dbutils the jobs the task value. Then task A sets a value, task B reads it. This is particularly useful for conditional logic. Then task B might decide to skip processing entirely if task A reports 0 new records. Now, the second one is for each task. For each task is a game changer for workloads that need to process a dynamic list of entities in parallel. So imagine you have 50 university departments, each needing their own data refresh. Without for each, you would need to either write a loop inside a single task, which cannot be parallelized efficiently, or manually create 50 task definition. But for each, you generate the department list at runtime, and Lakeflow Jobs finds out to process all 50 in parallel without a configurable concurrency limit. Now, a spot instance deserves a mention for cost optimization. For non-time critical batch jobs, historical backfills, model training runs, weekend analytics, a spot instance can reduce your compute cost by 60 to 80%. So the key configuration is spot underscore with fallback, which tells Databricks to use spot where available and fallback to on demand if slot capacity is not available. So never use pure spot for jobs with, of course, SLA requirement. Let me close with 5 things I want you to walk away with today. Now, number one is serverless by default. So stop creating job clusters for everything. So serverless eliminates startup latency, reduces cost, and removes cluster lifecycle management. So start there. Number two is the modular task. The monolithic notebook approach will cause you pain in production. Decompose by concern, design for retry, and you will thank yourself the first time a single task fails and you can repair it in 30 seconds or half a minute or a minute, rather than rerunning the whole pipeline. Now, number three is Git back source and asset bundles. This is the maturity threshold between a team that has jobs running in their workspace and a team that has a data platform. Version control, code review, and CI/CD deployments are not optional in production. Number 4 is resilience by design. Retry policies, timeouts, and concurrency limits should be in your job configuration template. So these are not advanced features. They are table tasks for production workloads. Number 5 is use the built-in observability, run history, repair run, duration alert, everything you need to operate Lakeflow jobs in production is already there. You don't need a separate monitoring stack for most use cases. So if you want to go deeper, subscribe to DataMindAI channel and drop a question in the comments. Read them, I read them all. So thank you for listening. See you next.